So hello. Before I get started, I've been trying to talk to some of you before, but I just want to get a little feel of your previous experience. So, quick raise of hands, how many are either doing iOS or learning iOS? Good. And how many of you are in any way doing Swift? It's more than expected. Is there anyone who's never done Objective-C? This was completely new. A few? Is there anyone who's been doing Objective-C since, like, from the beginning, since the iPhone was introduced, like the App Store? That's more closer to what I expected. That's roughly how I started. I got myself a 24-inch aluminum iMac and started learning Cocoa development, listening to podcasts like Late Night Cocoa, roughly around the time that the first iPhone was introduced. And this was the time before blocks and ARC and native JSON parsing. And around that time, it was the use of dot syntax was a highly debated topic within the community. But we have come a long way since then, both technology-wise and also as a community. Up until about 2 years ago, when Swift was introduced, I didn't really know anything about functional programming. And I suspect that a large portion of the community felt the same way. From the beginning, approaching Swift in isolation and in a playground always felt easy enough. It was easy to grasp. But then, actually using it together with existing code became a very different story. And that's what I'm going to talk about. A little bit of how we can use and approach functional patterns and integration with both our existing code and with Cocoa. And while preparing for this talk, I tried to think of the things that I could say that would be most applicable to others, not only today, but then also going forward. Because much of how we are currently dealing with Cocoa and existing code is highly dependent on the current state of interoperability between Swift and the Cocoa APIs. And both of these are evolving at quite a good pace, actually. And later this fall, when WWDC comes around, any solution that we have that is specific to how that interoperability works today might need to change or might have been made irrelevant. And also, some of the specifics of how we on our team are dealing with our existing code does depend on that existing code. So, in the end, what I'm mostly going to talk about is actually thinking and about some of the ideas, as I see them, that we are moving more and more towards. And what we can do and how we can benefit from those ideas today, while still working well with our existing code and with Cocoa. And as we saw before lunch, abstract thinking can also be an important aspect of software engineering. You could say that this talk is going to be a little bit of a functional programming talk, but coming from a converted Objective-C developer. And I have no question that Swift is where we're heading as a community, because it's simply, in so many ways, a more modern language. But right now, I feel that the most underestimated feature of Swift, and also, in a sense, its most important feature, is the interoperability with Objective-C and the Cocoa APIs. Because without it, none of us would be building or shipping applications for either iOS or the Mac, or now also tvOS and watchOS. But then on the flip side of that, the interoperability is also the biggest thing that is preventing us from fully embracing all of these new goodies, all that's new and great in Swift. So in a sense, it's more of an evolution than a revolution, and we just have to deal with that. As a result of this, it's quite easy to end up writing what is mostly Objective-C code, but in Swift. And this is some of the code that I've written in the past. So I know firsthand that it's very easy to fall back onto what is very familiar. And if we go down that path, then we haven't really gained much of the transition. But it's also important to note that we haven't lost anything either. Because in programming, we encounter a problem, and we apply a solution to that problem. And the Objective-C solutions are still solutions to the problem. Any new alternatives hasn't invalidating previous alternatives. It has just given us more choices to consider. And as with many things, when trying to open up to new ideas, it helps to start by identifying and acknowledging our own preconceptions. In this case, that everything is an object, which in Objective-C was very much the case. That's not necessarily so in Swift. In fact, in the standard library, very few things are objects and classes. And the types that we do interact with the most, such as numbers, optionals, array strings, dictionaries, set tuples, enums, they're all value types. Though in practice, there are still many things that need to use objects. NS coding, key value observation, a few other things, they simply depend on it. The runtime depends on it as well in many cases. And the alternative would be to find or build replacements for all of these technologies that then in turn work with value types. With our team and the project that I'm working on, we did not go down that path, but we still wanted to see what ideas from Swift we could use and how that could benefit our code. And even if we either won't or can't take any concrete action from it, identifying our own preconceptions do help us become more open to new ideas. Swift draws inspiration from many things, but among them, functional programming and languages like Haskell. But unlike Haskell, Swift is not a purely functional language. It is also an object-oriented language and a protocol-oriented language, and many other things for sure. And the interesting challenge that we as a community have ahead of us is finding the right balance between all of these different things and mixing them into something that is greater than the sum of the parts. As I see it, based on what I've learned over the past 2 years, the two ideas that from functional programming that are best to start out with are immutable data and pure functions. Both of them gives us a greater ability to reason about the behavior of our code. And they are both restrictions on our code that once created, a value will not change, and that a function takes input and gives us output without any side effects. And also that for a given input, the output will always be the same. Both of these things are fundamental to functional programming, but there is nothing in them that makes them unique to it. The thing about them is that in making these restrictions, we limit the possible behaviors of our code, which makes it easier to reason about what it could be doing. By ruling out mutation, then we don't have to consider what would happen if an object changed while we were working on it. And by ruling out side effects, we can take a function call and consider it equivalent to its return value. By having every argument passed to a function and knowing that there won't be any side effects, then we don't have to consider the order in which functions are called, because they can't cause any side effects, and we know that all the arguments are passed into them. So it will be safe for us to change the order as long as the arguments are available before they're called, but the compiler will help us with that. And also by knowing that the same input will always yield the same output, we can safely cache a value that is expensive to create without that value ever becoming invalid. Of course, being too restrictive will prevent us from solving the problem at hand. But on the other hand of that, the unused capabilities still come with some of their added complexity, even if those capabilities are not used. So it comes down to being as restrictive as we can, but then no more. And if we can do without mutation and side effect, that goes a long way in simplifying our code. The thing that both of these are trying to solve is shared mutable state, with emphasis on the sharing. And shared mutable state can make code really hard to reason about, and also quite hard to debug in many cases. And I'm sure you have experienced the effects of this sometime in the past. I know that I have for sure. It could be chasing down where a value was mutated, or just wondering why the state ended up in a way that you did not expect it to be. Immutable objects addresses this by simply not being able to mutate, and pure functions addresses this by not causing any mutation. Another way of being more restrictive, even though it might sound like the opposite, is to require the least specific type that we can for a function. So for example, if all we care about is comparing two elements, then all we really need from them is that they are the same type and that the type is comparable. And doing this is generally good practice. It makes functions more reusable, and you could even argue that it helps the function focus on a single task, because there are less things that can be done with that type. In object-oriented programming, this is called the interface segregation principle, that no client should be forced to depend on methods that it does not use. And it is one of the 5 solid principles. And I really urge you to look at the other principles as well. They apply very well to many things. They apply almost equally well to functional programming. Sometimes they have slight variations to them and they go by different names, but the basic ideas are the same. And in Swedish, and since I'm a Swede, there is a proverb for this that goes, "Ett kärt barn har många namn." And that roughly means that someone or something which is liked or well thought of is often referred to by many different names or different epithets. So in Swift, we can follow this idea or this basic principle by defining protocols that describe only the things we need and nothing more, and then taking the objects that have this functionality and making them conform to that. This is one of the examples from our code, and it makes it so that various components of our application can make decisions based on whether or not any part of the UI is visible to the user, without these parts also having to concern themselves with the many other capabilities of NS application. An added benefit of doing just this is that it makes it easier to mock or stub or in any other way replace these objects in a test, because we can know that they're only using these more limited capabilities. And we saw another example of this in Ruth's talk with the cell view model representable protocol that describes only the information that that cell needed from the view model. And when there are fewer things to consider, when we have limited ourselves or restricted ourselves, then we can sometimes start noticing new things that we didn't think of before. And one of those things are partial functions. And a partial function is a function that where not every input has a meaningful output. It can be something as simple as division, where division by 0 is not well defined. Another way of putting it is that the function has preconditions. In the case of division, that the number is not 0. Outside of functional programming and also outside of API design, you don't really hear much about partial functions. And that's not because preconditions don't exist. It's quite the opposite, actually. But it's mostly because we consider only a narrow set of the input and then seldom any of the implicit preconditions that come from the state of the object itself or the state of any of its dependencies. For me, identifying preconditions and then also starting to think about partial functions has made me look at code differently, trying to see what I could change and how I could restructure the code to minimize the number of preconditions, or if I were able to completely eliminate them. And it also helped me put a name on some of the things that I've in the past felt was off-putting about some of the code that I had written, but I didn't really know what the problem was. In some cases, if there's a precondition that state has been set, then we can ensure that it has been set by taking the state and passing it as an argument. And in doing so, we are making the code simpler in the literal meaning of the word simple, since now there are fewer cases to consider. It's only the case where the data is available. And passing dependencies as arguments like this also makes them more explicit. And then if it turns out that there's a large amount of arguments to a function, that could be an indicator that the function is doing too much or other complexity-related problems. So a very simple example of this, instead of first setting the username and password, maybe binding them to text fields in the UI, and then calling sign-in, we could change the sign-in method so that it takes both the username and the password as arguments. And doing so eliminates the possibility that sign-in is called before these two preconditions are met. And doing so leads to safer and more well-defined code. Good. And methods like this, even though they're not pure functions, can be, and because of state, often are partial. So, sign-in method, no return argument, surely does lots and lots of mutation, but we can still apply these ideas to it and benefit from them, even if we don't take them to the total. For functions that do return something, that might be might be pure functions, one way to make them into total functions, where every value has a meaningful output, is to change the return type to be an optional type. An option type comes from type theory originally, but it's used throughout in programming. And it's a type that represents either a meaningful value or the explicit lack of a meaningful value. And this is adopted in Swift with a question mark, and if you look it up in type theory, it's the same thing with a little question mark at the end. So it's not a coincidence that Swift chooses to do it this way. And also very much in Swift's spirit of safe code, optional types enforces the handling of both the case where there is a value and when there isn't one, as opposed to just making it possible to set a value to nil. And because of the quite recent addition of nullability annotations in Objective-C, and also the way that the nullables in Objective-C bridges to optionals in Swift, for the most part, it's really easy to use optionals in Swift, even when integrating with Cocoa or other existing code. Apart from a few minor cases, like an optional primitive can't be dynamic because it couldn't be represented in the Objective-C runtime. So for the old code, if you have existing code and it uses magic values like empty strings or -1 to signify that this property or this method does not return a meaningful value and is not found, could be one example. The way you can do is you can refine these methods by adding this nice little attribute at the end of that Objective-C declaration. You can refine them for your Swift code so that they return optionals in Swift instead. And in doing so, the compiler will help you to protect against accidentally forgetting to verify that the value was actually valid and then passing it along to something else. And that something else might have a precondition that the number is found, that the range is valid. And doing this, again, can lead to safer and more well-defined code. One of the things that make functional programming very expressive is higher order functions. And in computer science, this is sometimes called first-class functions, but all it really means is that a function can take other functions as arguments, and a function can return functions, and also that a variable can hold a function. So it's just like any other type. It can be passed to functions, returned from functions, be held by variables. And this comes back to one of those cases where not everything is an object, where a piece of functionality or a piece of logic can simply be a function or closure. And because of blocks in Objective-C and the way that they bridge to closures in Swift, for the most part, it's really easy to use higher order functions in Swift as well. Again, even when integrating with Cocoa and existing code. Taking functions as arguments can be used to separate the context from the specifics of a problem at hand. And it can lead to very highly reusable functions because of this. As a simple example, sorting a list or a sorting function of a list can be written to the details of that data structure that it is operating on, given that it takes a function which compares through elements. And in that case, the main sorting function deals only with the context, which is the data structure, whereas the comparison function deals only with a specific problem at hand, how to compare two numbers or two strings or two person objects or anything. And if you've done lots of object-oriented programming before and you are familiar with its design patterns, then you might also realize that this can be used for the same type of problems that the strategy or command design patterns are used for, which encapsulate functionality, passes it along. And many problems do come up time and time again with only small variations to the specifics of those problems, which makes them really good candidates for higher order functions. One of the most common and easy to grasp of these cases is mapping over a list. How many of you have encountered map before? Or are you just tired? It's actually quite simple. It takes a list of one type, type A, a function from A to B, and it will return a list of B's. And it doesn't do anything that we couldn't already do with for loops. Or in some cases, we might even have been able to do it with just key value coding and keypads. But it's these things that it doesn't do that makes it simpler and easier to reason about. Because what we can tell from it is that each element is going to be mapped once without any inter-element dependencies. And the result is going to have the same length and the same order as the original list, and will also not mutate the original list. And by ruling all of these things out, we don't have to consider them when reading or writing this code. Another very common example is filter. It takes a list of some type, type A, a function from A to a Boolean, and it returns a new list with only the elements where the function returned true for those elements. Again, we could have done the exact same thing with a for loop, but the restrictions of filter that no element is going to be modified, that order is going to be maintained, means that when reading this code, we don't have to consider those cases. And because of the way that functions are added through protocol extensions to types like collection and sequence, we can create chains of these things using dot syntax, which allows us to describe a complex operation as a sequence of smaller operations, where the input from one is the output from one is the input to the next one. And there's a big idea here, which is composition, where you take small and simple things and you combine them into larger and more complex things, which in turn might be combined into even larger and more complex things. And it's a really simple idea, but it has a big impact on our code, because it gives us higher flexibility, and that higher flexibility becomes really important when we're dealing with really big complex systems, and also when dealing with change. Because it's easier to change a component than it is to restructure something which is big in itself. In object-oriented programming, we commonly talk about object composition, in which simple objects are combined into more complex objects. But in functional programming, we commonly talk about function composition, where a simple function is combined into, or multiple simple functions is combined into a more complex function. So again, there are two different adaptations, but the idea is still the same. Smaller things are combined into greater things. Some functional programming languages, like Haskell, for example, have something which is called first-class composition, which essentially means that the language in itself has an operator which composes two functions. Swift doesn't have this, but we could easily build one ourselves. This is literally all you need. It takes a function from A to B and a function from B to C, puts them together into a function from A to C. So if it's so easy, why wouldn't this exist? Well, in Swift, not all functions are a single argument, and they're not curried by default either. And also the functioning, the currying syntax is going away. So this operator wouldn't be that useful. Though that doesn't matter for the idea itself. Even if Swift does it differently, the point is not to mimic syntax or notation of a different language. The point of composition is to combine simpler things into more complex things. Yes, and even if Swift does that differently with protocol extensions, that doesn't make the idea any less valuable or any less applicable. So it is possible to do a combination of many things, like filtering and mapping, in the body of a for loop, which for most of us is going to be a very familiar solution. But there's also all of these higher order functions that can be combined to do the same thing. So the question becomes, when would we use one or the other? And more importantly, why would we do that? And of course, with any such question, there is no definitive or absolute answer, which is why the why and the nuances of the why is so much more important than the answer itself. The best that I've come up with is that they differ in style. The higher order functions are more about the what of the problem, whereas the loops are more about the how. In other words, it's a declarative style and an imperative style. Same as with Rx. The higher order functions and composition scale by composing multiple what, whereas loops scale by adding to the existing how. And if the total of the problem is very complex or very likely to change, then the flexibility of composition and also the separation of smaller components, breaking the problem up into smaller components might provide real value. But if the problem is too small, then none of that really matters too much. And it mostly comes down to a general argument about declarative versus imperative style. I, for myself, like to focus on the specifics of the problem, if I can. I feel that it speaks more to the problem being solved by first describing what it does, or possibly even naming what it does, and then following up with the specifics of the problem. So I choose to favor the declarative style. As an example, if we have a list and we want to combine a list of values into just a single value, one example would be summing up a list or finding the largest element, or having a list of conditions and we want to check if either any of them or all of them are true. Then that is a reduction from a list to a single value. And we use reduce with a function that operates on each element in the collection together with the accumulated value. And that builds up the result, which at the end of the collection is, in this case, the sum of the list. As to what we are operating on, if we want to operate on indexes and elements together, then we can use enumerate. If we have two collections and we want to operate on them as a pair, then we can use something which is called a sit. If it's just arranging numbers, then we simply use arrange. And if the increment is different than 1, then we can use what is called a stride. And we can also do that if we're operating on floating point numbers. So in each of these cases, we can either loop over it, or we can use map filter and reduce, or a composition of them to do something with it. And what we end up doing mostly depends on what's suitable for the type of thing that we're doing. Performance is one of those things that might come up as an argument in favor of loops and in favor of imperative style in general. But I would be very careful to jump to conclusions about performance. It can feel quite intuitive that the higher order functions, because they're a higher abstraction, and because there's multiple function calls involved, and might iterate over the list multiple times, and possibly other things, that they should be much slower than what a for loop would be. But my experiences so far has been that all of the restrictions that we put on our code, so all of the things that the code can't possibly be doing, also provides a great deal of information to the compiler, which allows it to take greater liberties when optimizing the code. So, in the end, the compiled code might not be that different at all and might not perform differently at all. But as always, with performance, measure, and preferably try not to optimize before you actually find a problem. At which point you do, start by measuring. There is one clear case for loops and other iterative constructs, though, as I see it. And that is code which is mutating and code which is explicitly causing side effects. Trying to do that with higher order functions is simply a bad fit, because they try so hard to avoid it. So that's a clear case for using a loop. Also, cases that break or continue halfway through or do early returns might, because of familiarity, just be simpler and more straightforward to do, to implement using loops. And that roughly summarizes the when and what that we settled on our team, that we try to use and compose declarative style functions where they are available and where the code is free from side effects. And from everything else, we use for loops or other type of iterative constructs. And in doing this, we set some expectations that when you're reading through the code and you encounter a for loop, that you can either expect it to be causing mutation or do some type of more special or irregular kind of iteration. Luckily, there is one place where we can use pretty much every new and exciting feature that Swift has to offer. And that's in the private implementations of things. As long as the boundary which most likely is the interface of an object, remains compatible with the rest of the system, then the implementation could really be anything. And that's the basic principle of encapsulation. In particular, there are two things that you can do with this that I'm going to focus on, and that will be separating data and separating logic. Sometimes, quite commonly with custom drawing code or animation code, all of the configurations of stroke widths and paths and colors and keyframes and timing functions, they can really clutter up the code. And this is especially true if the drawing is very complex or if there's a chain of animations that operate in a sequence. And one of the things that we found is that by using private structs and enums and other small value types, we can create these little one-off data types that are tailored to the needs of that specific code. And this is one of the examples from our code. It's a low activity indicator with a custom animation. And this is the entirety of its code. I don't intend for you to read it. It's at font size 3. But I'm going to point out a few things about its structure. And that is that by creating 3 enums that are private with associated values, and then a private struct to hold different combinations of these enums, we were able to separate the data from the rest of the code. And these blue regions are only the data, so where it's calculated and where it's initialized. And these data types are written to serve the animation code with keyframes and timing functions, which makes it so that the animation code in itself, maybe that's too small, the animation code in itself can be as simple as possible because it doesn't have to concern itself with these things. And this is slightly different from creating a style or configuration object that is public, that you pass around, because these things are really private and tailored for a single implementation. So they can return the data in the format that the code wants it. So the code wants scaling values, key times, and timing functions, and these little data types can calculate them and have properties that return the data in the format that the code wants it to be. Other times, there is some code that has a lot of different rules to it, and quite possibly also many exceptions to these rules. And it just complicates other code around it in the application. I'm sure you have encountered this before. One such case in our example is what people gets shown during a group video call, and then also in what order they appear. There's a lot of rules around that. And I won't bore you with the details of how that gets decided, but the key is that this logic doesn't really belong in the views, but it's also presentation related, so it doesn't really belong that well in the model either. And most importantly, there's a lot of rules, and we would like to test all of the cases, especially the corner cases, if we can. So what we ended up doing in this case is that we moved all of this logic into a single place. And then, internally, we implemented it using 2 custom value-typed data structures that are quite general and operate on anything equatable. And then the wrapping object exposes a dynamic array and implements the key value observation compliance and makes sure to do the correct insertions and deletions. And the wrapping object is mostly a skeleton that manages state. And it can do this because it can call down to functions that are tailored for its needs and return the data as it needs it. So for example, function that returns both the change kind and the indexes, which the wrapping object then uses to call will and did change values at indexes for key. The benefit that we found in this case was that, first of all, it moved the code into one place and moved some of the code out of the views and some of the code out of the models. But more importantly, that it created a very testable implementation. And that, for the most part, that implementation was separated from the actual people and call classes. So most of our test code ended up looking like this. And in this case, it's just using strings, because strings are equatable. And funny thing that I'm just going to summarize very quickly is that less than a week before giving this talk, we were told that the designs had changed just slightly, and that never happened before, right? And that, well, some of these rules would be great if we can change them. And since they are well isolated and well tested, that won't be as problematic as it might have been. So, in conclusion, if you only ever done Objective-C or other object-oriented programming before, then Swift brings a lot of new ideas to the table. And even if we're not able to use all of these new tools with our existing code as things stand today, the ideas themselves are very general and are generally applicable. Things like immutability, pure functions, requiring the least specific type, composition is a big one, functions as arguments, and also thinking about ideas doesn't only apply to functional programming. You can approach many things with the same mindset. What if the ideas behind MVVM or reactive programming, even if you don't use them as tools in your code base, you can still evaluate the ideas and see how those ideas can benefit in your code. And also that by learning new things, we are in a sense adding substance to ourselves and growing as a developer. So I'm going to end things with a quote from Alan Perlis, who is the first ever recipient of the Turing Award. And it goes, "A language that doesn't affect the way you think about programming is not worth knowing." Thank you so much for listening.
Hello. Okay. Thank you. So I see we have questions already.
Hi. So my question is in the context of composition that you talked a bit. What is your opinion about Apple's NS operation? So that's the first question. What is your opinion about it?
I like it generally. It's really good for certain things. I don't know if you just saw, there was a WPC talk about it last year, where they composed like entire UIs and did logic using operations so that you could, for example, not show more than one alert at a time and put up dependencies between operations. I think it can be really powerful, but it's not used widely enough.
And the second question, still in the context of composition, what is your opinion of the error handling in Swift with the try-catch in comparison, for example, with the optionals that you can compose and just...
So composition, well, that's a difficult one. In a sense, we're losing some functionality with the error type that we used to have with NSError. With NSError, you could always attach the underlying error and keep throwing that upwards the chain. So if you had a sequence of operations, you could still attach the information of the error if it was multiple levels. But then other things like result types that attach the error, they also usually end at the first error, right? And then just along the chain, you would get the point where it failed, not necessarily all the levels of the failure. Is that answer?
Yeah, thank you.
Any more questions?
I did. I again have questions. And I thought I'd just ask them if nobody else was there. So first of all, did I get correctly your slide with the tests that you actually replaced? So in here, you're testing how previews of people who are on a call will appear.
Yep.
By actually using strings because they actually exhibit the same behavior that you want to test.
Yeah, we talked to like our product owners and got them to basically iron out these rules as much as possible. And there was nothing to the rules of the system that was tied to the people. It was all, if this is the same object, that's that object. And with that realization, we could write the code so that all it needed was an equatable type. And then we could test it using the strings.
This is amazing. And could you give us some examples? Like, because you talked a lot about the conclusions that you drew. Could you put some of them in context? Like what kind of product was or what kind of feature of a product maybe some of these conclusions were drawn? Because I mean, come on, you work on a product that literally tens of billions of people are using. So it will be interesting for us to hear, like, specifically this happened, this was the problem. And
good question. So for context, I work at Microsoft on Skype and Skype for Business, which are used by lots of people. Calling is probably the area that has the most. Calling is an area that has lots of rules to it. It's generally like, I don't know, half of our code base or something. Most other things actually are the composition and the things we realize there actually comes from maintaining basic lists. Things like search results and filtering out the people who are removed, but then also doing a filter that collapses the list nicely. Doing simple things like seeing if you have any conversation with read messages. So a conversation might be unread or might have unread messages. And by reducing over all collections, you can get a Boolean of whether or not any of all your conversations have unread messages, or if any person in a call is speaking, or things like that. Basic maintaining a list and reducing many results into a single result. That has nothing to do with anything. That is applicable to almost any application.
Thanks for the presentation. I really loved it, and I have a very particular question. Do you think that actually learning concepts like the famous monad that everybody is afraid of gives you any great value of functional programming? It's about composing, and monads are kind of composing things in a way that you can be safe So what's your opinion about it? Is it worth to know what it is, or just use it and then, yeah?
So I'm conflicted about monads. I feel that there is some usefulness in knowing the type of problems that they solve, but I also feel like you can do very much with the much easier ideas of functional programming. And as long as you're not, as long as you're mixing so that you still have stateful code and objects in your code, then you can do perfectly fine without having to resort to monads as a strategy. But it still adds some depth to it, that it might feel that functional programming, if you only look at the basics of it, has a ceiling where you can't go any further. And that's where monads come in. So if you think about all of these basic things in functional programming, most of what I focused on here, when you feel like there's a type of problem that could not be solved using only those, then that's typically when you would use monads or applicatives, or like, the type of category theory stuff that's very predominant in purely functional languages. So it adds depth to it, but since it's not, unless you're doing purely functional code, you seldom need that depth, and you could use objects or stateful code to mostly solve the same type of problems.
Okay. More questions? Okay, so thank you, Dave.